All right, we're going to continue. I'd like to welcome Ella and Juan from Igalia, presenting improvements to the Raspberry Pi GPU driver stack.
Thank you. So, good morning, everyone. My name is Juan, and with me is Ella. We both belong to the graphics team Igalia, which basically works across different drivers. But for this presentation, we will focus on the enhancements we did for the Raspberry Pi driver, for the MISA 3D driver. It's important to highlight that we basically are presenting here not the work done by us, by Ella and me, but also for other members of the team graphics that works on the improvement of the Raspberry Pi driver. So, what I'm going to show here is basically in two parts. One is the features we are developing for the Raspberry Pi driver, specifically for the GL driver called V33. And then we will show some work we did for improve the performance in the same driver. And finally, we have some questions. So for the first part, Ella will introduce this part.
Over the past year, we've implemented quite a few new extensions. This is a summary of the ones available in the 24.2 branch point. I'll go over in more detail the ones highlighted, along with a couple other features we've implemented as well. Firstly, frame buffer fetch. This was quite a simple one to implement, where we just lower the load output instruction to the V3D specific TLB intrinsic. And by implementing this, we get advanced blend equations from Gallium. This feature is an important prerequisite for some of the later work, as it's required by the near lower blend pass. Next, we implemented dual source blending. This is a feature heavily used in emulators, and the example shown on the slide is of Mario Kart running in Dolphin. When dual source blending isn't available, we get some very interesting rendering issues. As you can see on the left-hand side, it displays as a completely blue screen and is very much unplayable. Unfortunately, the hardware itself does not have support for doing much in the way of blending other than the very basics. So we needed to implement a software fallback, and for doing that, we use the common near blend lowering pass. With that implemented, we get a playable version of Mario Kart. And next up is 16-bit normalized formats. For these, the hardware also doesn't support them at all, but we do support 16-bit integer formats. And we can emulate normalized format support by adding pack and unpack on every load and store output instruction in the shader. Unfortunately, we also need to use the same software blend fallback as we did for dual source blending, since the hardware would not have any native support for the normalized formats in the blend hardware. The hardware also doesn't support blending of 32-bit float formats, so we also use the software blend fallback there. We also added support for near printf, which is a very useful debugging feature, which allows printing from within the shader onto the console. It's quite verbose, however, in the information that it gives, since it prints information for every single invocation. So we added a new helper to print only information for a single pixel. This I found very helpful when debugging some CTS issues related to the dual source blending, where the Vulkan driver initially wasn't passing all the tests, and it ended up being an issue with how the CTS was calculating the expected results of 3-component formats. We also implemented support for robustness. Newer versions of OpenGL CTS require support for robustness to run with the terminate on device loss flag, and this has become the default. If you run CTS with the default configuration on the Pi before implementing this, it would crash without any useful error message. This was done by adding reset counter support to the kernel driver to keep track of how many times the GPU has been reset in the current context and globally. We still have some pending features that need to be implemented for OpenGL 3.2. The main one is non-seamless cubemap support. The hardware only supports GLES-style seamless cubemaps. There is a lowering pass in Mesa used by Zinc, which tries to emulate non-seamless cubemaps by using texture arrays. However, using this pass doesn't pass all pigless tests and gets into some very odd edge cases with MIP levels and filtering. I'll now hand over to Juan for talking about performance improvements.
Yeah, so besides the work that Ella was mentioning, and also, of course, working on the bugfixing and things like that, one of the things we're trying to do was improving the performance of the driver. Basically, we focus on the OpenGL driver because this is the driver used by the desktop, and we were trying to improve and search for scenarios where the EPU was the limit part, especially using the Full HD turret, which is most of the resolution that people uses. For this, we are using several traces from GFX Bench, which are popular Android application to run benches. I say traces because we are running in Linux, so we use these traces with API-trace to investigate what is happening, and with that, we basically try to optimize the driver. And with the last change, last changes down since the last XDC, we basically get an average improvement of 32%. It really depends on the trace. For some traces, like almost 5%, but the one is almost 70%. All these performance optimizations are already available in the latest Mesa stable version. And in the next slides, I will explain some of these improvements and how they did affect each of them on the performance. So the first improvement happens when we have invalidated frame buffers. Before these improvements, we were running all the tiles, and when running the tiles, there is a step of loading the tile buffer, and then other step with storing the result of the tile buffer. But when we have invalidated frame buffers, it doesn't make, it's not required. And the loading and the store is quite expensive operation. So basically, just avoiding doing this, we get an improvement of 1%. Maybe this is not much, but this is because on the trace we were using for GFX Bench, there is no many cases where the frame buffers are validated. But for instance, in Chromium browser, using, for instance, the Google Maps, there are quite a few invalidation of frame buffers, and in this case, the performance is really noticeable. I added here a reference to the commit that implement this optimization. The next one was optimization with the early depth testing. Before this, basically, when there was a discard in the front-end shader, we basically disabled the early depth. But then we realized that if there are no depth writes, actually, and well, not only depth writes, but also there are no occlusion queries, basically you can enable early death even if there are discards. With this, we get an improvement of 13% in average of the frame buffer, frame per second. That goes from mostly 5% to 20% because there are some of the tests, some of the traces really goes through this kind of situation where they have discards, but they don't touch that buffer. So we can basically re-enable the early death. Another improvement we were doing was is also affecting the load stores for the type buffer, and this happens when we have the rasterization disabled. So in this case, as we are not going to run the rasterization, basically we can avoid, like in the case of the invalidated frame buffers, we can basically avoid doing the stores and the loads. And again, this kind of avoiding the load stores in the type buffer have quite a big impact. In this case, goes from 13% in average. In some traces it doesn't affect, but in others like a 40% of average of improvements. And as I say, there is some of the cases where this is very interesting. Some here is like transfer feedback is used, but you are not interested in doing the rasterization, only in getting the transfer feedback and the geometry. And another one, this is probably the final one, is like a continuation of the previous one, which is basically avoiding the supertile coordination submission when there is no rasterization. So the thing is that even when avoiding the load stores, basically the supertile is basically like the set of tiles that are going to be processed by the GPU. And when we emit the supertile, basically all the tiles in the supertile will be processed anyway by the GPU. We are avoiding the load stores due to the previous commit, but they are going through the GPU will process all these tiles. So again, if we are disabling this rasterization, the thing is not emitting the supertile, which means basically that no tile is submitted to the GPU, so the GPU will avoid to run the process in the tiles. With this, basically, we add an extra improvements of 1%, is not much, but again, it varies a lot in between nothing and almost 40%, depends on the trace. So here in this slide, these are the improvement per benchmark and also the improvement per each of the commits. And C0 basically is the situation we have in the branch point in 24.2. I think it's basically during the last XDC. And the CM basically is the commit from the last week, I guess. So basically, this is basically the improvements between last XDC and this XDC. And you see basically there was improvements in all of the traces. In some of them are much bigger, like for the Manhattan demo is quite big, specifically due to the third and the fourth. I mean, avoiding the load stores when the rasterization is disabled. And yeah, and basically I think that's all. So any questions, welcome.
Thank you for a couple of questions. How much of it is already available in Raspberry Pi OS, like in official releases? And second question, how much of it is relevant for Vulkan, for example? Thank you.
What's in Raspberry Pi releases? I don't know.
Sorry, can you repeat the question?
Can you hear me? Okay. The first question, how much of it is already available publicly in Raspberry Pi OS, like official releases?
Okay, so for the optimizations is on the, it's in this stable version, it's already merged there, but I'm not sure, I don't remember because Raspberry Pi, Raspberry Pi OS is based on the Debian version, so I don't remember exactly. They are following, I think they basically depends on what Debian is doing. I'm not sure if Debian is packaging the last version or not.
So I believe that this is all merged in the latest update of the OS. Don't quote me on that, but I believe it's the case.
And the second question was how much of it is relevant for not OpenGL but Vulkan?
Okay, so all these optimizations can be applied to the Vulkan driver. I think some of them are already merged, already applied in the Vulkan. Others are not yet. I think the validate frame buffers thing is not in the Vulkan driver, I guess. But we are working on porting these optimizations to the Vulkan driver too.
Hi. So in terms of Ella's part of the talk, my takeaway was there's a lot of features that are not natively supported in the hardware and for which you provide software fallbacks. Did you need to make any kind of trade-off considerations there between exposing those extensions, which might be picked up by other games than the ones you were trying to fix, and which might slow them down due to being a software fallback, versus enabling things like Dolphin, for example? Like particularly dual source blending, I imagine, is somewhat expensive if a game were to accidentally use it when it's not hardware accelerated.
The emulated features don't really have that much overhead if you're not using them. I think with the 16-bit normalization stuff, that's probably the best you can do compared to what an application could do. I'm not sure about blend. It'll depend on the application, I guess.
Just to clarify, I was speaking about like if a game were doing a feature test and like it has an optional path for using dual source blending. Does that happen in practice at all, or?
Dolphin used to have a fallback for it, but they got rid of their fallback because their fallback was very painful. So I think the way that it's implemented in the driver is probably better than what an application would do.
Hi. I was just curious to explore how have you implemented the GPU reset event profiling and configuration, and if you are using it?
I'm not sure about that one. Do you know? Is it about GPU reset?
So how do we do it?
How's it implemented?
Yeah, so basically the implementation it requires kernel support. Basically the kernel have a way of tracking their GPU's issues because they perform a GPU reset. So we basically add like a counter that is counting wherever it is a GPU reset. And then from the user driver, there is a IOCTL call where basically we query what is the status so we can know if there is, we have the previous counter value, so we do an operation that we get the reset counter again and say, okay, there is a new increase in the counter. Okay, so there was a GPU rest, so we can tell into the application that, okay, there was a user space. Using different counters, you can even discriminate if the rest was caused by your own application or was caused by a different application. It's like, you need support from the kernel.
I guess so that's a full stack implementation between the user space driver and the kernel driver. Thank you.
So trying to reply to the previous question where they were asking if there was a penalty for the emulated features and whether we had considered the trade-off. I think there is a penalty, but I think depending on the feature, it's not going to be, we think, too bad, particularly for the case of dual source blending and the 16-bit normalized formats. We think it's not going to be huge, so it's probably much better than not having the feature and then having to do some other workaround in your application to get the effect or the rendering that you want to do using some other things.
Hello? Oh, yeah. Hi. I wanted to ask regarding the 16-bit normalization. I don't know if I say it correctly. In how far do you think could that be ported to other drivers in Mesa? Context here is that with like HDR work, etc., becoming more common, like more and more toolkits and apps rely on the Norm 16 extension to be able to, for example, upload like 10-bit video or something. GTK4 being an example here. And it would be super nice to have that extension like supported like in every GLES3 driver. And I was wondering if that's possible with your work.
I think the lowering pass could, for the inserting pack and unpack, could be ported to generic Gallium quite easily. I think some issues might come up with blend, but I'm not sure.
Is the OpenGL free exposure only available on the Raspberry 5 and above? Because I've heard the Raspberry Pi and older GPU doesn't have enough render targets to support OpenGL free.
Yes. The Raspberry Pi 4 only has 4 render targets. The Raspberry Pi 5 has 8. I don't remember off the top of my head exactly what OpenGL version starts requiring 8, but yes.
There's a clarification here because, right, for the OpenGL 3.1, it requires 8 render types, but it's not only the Raspberry Pi, but other drivers are only supporting 4 render types, and still Mesa is kind of cheating here and ignoring this and ignore that even for drivers that only support 4 render types, it exposes like support for OpenGL 3.1 if it implements the rest of the drivers. Because otherwise, probably most of the drivers won't be exposing the embed drivers, not the desktop drivers, but won't be exposing the OpenGL 3.1. So basically, this is something that Mesa is doing on purpose. So ignoring the 8 render types. I guess because most applications or most use cases only requires 4 render types. So very few applications will require 8 render types. And even in the CTS conform master suites, there is no test checking for the 8 render types. Only Picklin is doing that. So I guess everybody knows that. Well, it's fine if we do that.
All right, so we were a little bit over time already, so thanks a lot again, Juan and Ella from Igalia.